Hello and welcome to this quick little video that I want to make that talks about the daily tasks that we have done in class. Keep in mind that it's part of our requirement that we set up some sort of a presentation to one of these tasks. You can check that assignment on Google Classroom in order to get an idea of what I'm really looking for in there. And I just wanted to give this quick rundown because I know that there's students that aren't able to attend class live, so we should at least look at some way that we can kind of all be on the same playing field. So I'm probably not going to fully do many of these tasks, and I'm only going to look at the ones that we've done so far. So some of them I have no choice but to kind of really finish them out, but some of these they're pretty they're pretty limited, and some of them take a long time. Some of them are just an answer. So for this first one, we talked about the 4 4s. I want to combine 4 4s in a way that I can get the numbers 1 through 20. And we talked about a couple ways in class that we could do that. We could use addition, we could use subtraction, multiplication, division, probably include some sort of parentheses. Let's see what else. We talked about square roots. I don't know if we did it in class or not, but exponents can work. Exponents can work as long as it's the 4th power that we're raising it to. So one of these 4s would be an exponent, and the way you would write that in a line is, you want to write 4 to the 4th. If you want to write 4 to the 4th, the way we would write that, if we were stuck on one line of writing, is we would say that that's 4 raised to the 4th power. Okay. We talked about factorial in class. Somebody brought that up as a way to get some of them. And what 4 factorial means is 4 times 3 times 2 times 1. The last one that I brought up in class is, it looks like the parallel symbol from geometry. And what that means in math terms, it's called concatenation. And what it means is if I look at this symbol 4, that would equal 44. It sort of just means to kind of apply to the end of our string of numbers. Okay, and I can see some places where that would be useful, and some places maybe where it wouldn't. I'm actually going to use it on this first problem, and just to be sure, whenever I'm using that symbol, because it's not really a standard for order of operations, I should put parentheses around it. I would assume in order of operations, if it really showed up, it would have to be first, but just to make sure. So I'm going to use 4 concatenated with 4 divided by 4 concatenated with 4. That would make this 44 divided by 44. And that would equal 1. You could do 4 plus 4 divided by 4 plus 4, 4 minus, well, wouldn't do that one. But you get the idea there. So moving on, and like I said, I'm not going to do all of these because there's 20 of them, and I don't want to take the power away from you. This one is a really good one to get you thinking. This is a really, I know it sounds easy, but it's actually relatively difficult. So I challenge you to work through this if this is the one you want to present on. And maybe you're having a hard time with 1 or 2 of them, go ahead and email me, and I'll at least put my mind to it. I'm going to go ahead and say that off the top of my head, I don't know that I could do all 20 of these. And especially in the amount of time that I want this video to take, definitely not. So, obviously the math level is a little bit lower here, but sometimes it's a little bit harder to explain each one of them. The second task that we talked about was called shapes. Okay? And this task was all about how do you see things growing? There really was no question to be answered. It was just, there is a question, I guess, but there's no numerical answer that this task is really looking for right away. I know we posed one in class, and that's great, that's fine. But really this task is about you describing how do I get from picture 1 to 2 to 3. And there were a lot of things. I sort of had to bring up a lot more ideas than students really did in class, because I think everybody kind of sees it growing the same way. But I would say that there's a lot of different ways that we could visualize this growing. Sort of the first way that I think of, and maybe it's your first way, maybe it's not, is sort of it's sort of like a bottom-up approach, but it's formed the other way, even though I say bottom-up. I think of it as the raindrop method, where I'm going to take, actually let me move this up. I'm going to take 5 more squares, and they are going to drop down. And wherever they land, if they land on top of a square, then they sit on top of that square. And if they land on the ground, then they land on the ground. And that's how this next picture is built. So I mentioned that in classes as being called the raindrop method. Okay? And that way works. That way is, if that's how you see it, then that's how you see it. There is no right answer there. It's what do you see? Now, if you're presenting this task, I would expect that you talk about at least 2 ways that you see this growing, because we can't always anticipate how, like for me, when I'm teaching this task, and that's really what I'm looking at you doing when you're presenting these, is kind of teaching them, not just saying, hey, my answer is 7. I'm looking at you really getting into that mindset of what is this like through someone else's eyes. So like for me, whenever I'm doing this task in a class, which I've used it in classes before, I'm never just saying, well, this is how it happens. I have these 5 squares on top, they drop down. Then I have 7 squares on top, and they drop down. Then I have 9 squares on top, and they drop down. That's not what I'm saying. I'm saying, how do you see this thing growing, you personally? So that's one way. Another way that I see is sort of adding a row to the bottom and making sure to extend the sides by 1, because I need that single block on either end. So that's another way, and I mentioned that as like the bowling alley method, because it kind of looks like a set of bowling pins, and how if I added a row to the back of the set of bowling pins, I'd have to add them in just the same way. So that's another way. And then there was kind of another way that I brought up that I've actually had students tell me in the past, was that they took this and sort of flipped it over on the other side of this single block, or the next, you take the sort of half of this, or the better half of this, and you copy it down over here, flipping it over. And then this middle stack has to grow to 1 bigger. Okay, kind of a more laid out approach to it, more involved approach, I would say, but it still works. If that's the way that you see it growing, then that's the way you see it growing. And then sort of bonus points, if you think of it this way, and you, instead of thinking this as a pyramid, you start thinking of it as a square, and then you're kind of taking this upper part here, the lesser of the square, and moving it to here. If you don't believe me that works, try it. Try putting these 3 squares into these 3 spots over here, and you see that you get a square, move it over. That one's especially helpful with the extension question that I asked, which was how many squares in the 100th figure. That doesn't look like figure to me. But how many squares would be in that 100th figure? So that was the extension question that I asked. It's not the question that this is asking you to answer, but that was the extension that I had. So again, in all of these tasks, it's important that you come up with the extension that makes sense to you, that you would want to ask your audience. So maybe it's not the 100th. Maybe you're mean and you want to say what, the 1,000th or the 1,000,000th picture. And then we're just, like I said, we're just kind of getting mean there. But, think about your extension question and think about a good question that you can ask. The next one we looked at was called bouncing off the walls. It says that Timothy must get from point A to point D, but at some point along the way he must touch this other line BC. And the question is, what's the shortest route that can satisfy these conditions? And this one's a tricky one. I'm not gonna sugarcoat that for anybody. It's a really tricky question, a tricky task, and it really comes to the idea that in order to make the shortest distance between 2 points, it would be a straight line. We all agree with that. So the idea is that I want this trip to happen in as straight of a way as possible, which means that I want to straighten this out, or think about what that means for that section to be straight. Okay, and it really comes to thinking about this down this way. Yeah, that looks bad. Try that again. Oh. What are we doing here? Come on. There it is. So if I think about this 10, I'm guessing, we don't have any units here, but if we think about this 10-foot wall being down here, I want to know the shortest distance from this point to this point down here. Well, that would be a straight line. We would want that to be a straight line in order to argue that it was the shortest distance. And it's really going to say that even though we want to sort of ricochet off this wall, the shortest distance would be if I flip this wall down here, this would be my shortest distance, and whatever this length is would really just be the same as that. And that takes a little bit of geometry, kind of some proof stuff that I don't really want to get into. But now the question is, how far is it from point A to this reflection of point D? And we could call that D prime if we wanted to. What is that distance? It would be the same as the distance to this intersection up to D. So I'm going to leave it there for you to figure out what is this distance from A to D prime, and that would be your answer. And then you can think about reflection questions, and maybe you would think about, or not reflection I guess, but extension questions. Maybe you could ask, like, what would the longest distance be? And that would be, I think, a pretty good question to ask. The fourth one I think we're on is from a movie. The movie is Die Hard with a Vengeance. And it's just a sort of riddle problem a little bit, but it says that these two people are trying to defuse a bomb by placing exactly 4 gallons of water on a scale, and they have two unmarked containers, so they can't tell, like, the unmarked part means oh, we'll fill this up halfway. You don't know where halfway is, so we can't do that. But one holds 5 gallons, one holds 3 gallons. They have an unlimited amount of water, but they have to get it right on their first try. How can they be sure to only put 4 gallons on the scale? And so we've got these two containers. I thought I had them down there, but that's okay. And it involves like, fill this bucket up, pour it into here. What does that look like? And I would urge you to kind of take like a step-by-step approach to this. If you can use visuals, use visuals. I think it would be really cool to actually see somebody have a 5-gallon bucket and a 3-gallon bucket. They make those. That would be really neat, but I wouldn't expect that. But find a way to sort of draw it out and talk about, okay, so I did this thing. I poured the 3 gallons into the 5 gallons. So, and this is what I did in class. Pour the 3 gallon into the 5 gallon. And so then what it looks like is I have my 5 gallon bucket and my 3 gallon bucket, and this is empty, and this has 3 gallons. Okay, now the next step, I'm going to do whatever, and then the situation is going to look like this. So then I'm redrawing something, and it's just a step-by-step process. I'm not going to give it away. If you have any questions, if this is the one that you really want to do, but you're unsure how to do it, go ahead and send me an email, and we can talk about it. The 5th task that we talked about was called Barbershop Quartet, and it's talking about a barber that wants to paint a red stripe on the white pole outside of his business. So if you've driven by a barbershop and you've seen the red and white pole outside, this guy's only got a white pole and he wants to paint the red stripe on it, even though there are black stripes on here. I don't have a color printer, I guess. His pole is 20 feet tall with a constant circumference of 3 feet, and the barber wants to wants the red stripe to wind around 7 times as it reaches the top. It says here what is the area of the pole to be painted. I don't know if you're really equipped to answer that, but there's a lot that you can do. And I'll talk about what I mean in just a second. So I have 20 feet here, and I know that I have a 3-foot circumference. So we have to decide what's going into, let me actually make it a red stripe. What's factoring into this red stripe, because it has a vertical component as well as a horizontal component. It's going sideways and it's also going up. So I'm just going to try to straighten that, sort of take that wound up stripe and sort of unravel it and look at what factors into figuring out how long it is. That's the main question that I'm going to answer, is how long is the red stripe? I think when I was typing this, I was thinking about an extension with what is the area of the pole to be painted. And this is the question that we answered in class, so you're not getting like a different version of what we did. But again, as with a lot of these problems, sadly, we're dealing with a Pythagorean theorem problem. Whoa, sorry, I thought that was a line. We're dealing with a Pythagorean theorem problem, so I want to know what goes into the vertical and what goes into the horizontal components of this line, of this red stripe. Well, the vertical distance that it travels, it goes from the ground, or 0, to 20 feet. So it covers 20 feet. How far does it travel going horizontally as it winds around this pole? Well, it goes around the pole 7 times with a 3-foot diameter, 3-foot circumference. So really, this horizontal distance is 7 circumferences, which is 21 feet. So I think from there that you can use Pythagorean's theorem to answer the question of how long is the red stripe. I think it would be a really good extension if, let's say he wanted to paint the red stripe, could he paint it 2 feet wide? Could it be a 2 foot wide stripe and make it to the top? I mean, it should always make it to the top, but obviously there's some thickness of this stripe. I'm saying, like, if this was maybe 5 feet, it might turn it into a red pole instead of a white pole with a red stripe, if that makes sense. I guarantee you if it's 10 feet, you're only going to get 2 trips around and it's going to be all red. So 5 feet might actually, no, 5 feet won't work, sorry. So you have to ask yourself, like, what is a reasonable thickness of a stripe? Or you could look at, let's say he wanted to paint it, he wanted it to end up half red and half white. What kind of a thickness of a stripe would that have to be? So there's a lot of good extensions on that one. I'm going to leave it to you to pick the one that you want to do. Okay, the last one we're going to talk about is the task that says this ain't no hill. Talking about Jack and Jill going for a run, having a little race, but they have the same walking speed and the same running speed. This is all kind of coming down to the idea that distance equals rate times time. Pretty common equation in physics or whatever. Just in life. I mean, if you want to get somewhere faster, then go fast. If you want to get somewhere in less time, then go faster. But yeah, they decide to have a race. Jack runs half the time and walks half the time. So we need some variables here. Jack runs half the time and walks half the time, and then Jill runs half the way and walks half the way. Who wins the race? And I'm going to give you a hint to say it's the same person every time. Okay? So this is the same person every single time. The question comes, who's going to win? And you would think at first glance, like, well, they're going to tie because they both run and walk half the way. Well, not necessarily, because Jack runs half the time that it takes him and walks half the time that it takes him. Jill runs half the way and walks half the way. So let's get some variables here. I'm going to let capital D stand for the race length. I think that's the best way to say that. And GTH. I'm going to let R, since they both have the same running and walking speed, R is going to be the running speed for both Jack and Jill. And W would be the walking speed. And then we also need the variable T for time. Because if we're looking at who wins the race, that means the shorter time. And so we're really trying to see who has a smaller T value, a smaller time value. So if we look at this, for Jack, he runs half the time and walks half the time. Now since since the race is going to be, since this capital D really is going to equal a rate times a time because it's a length or it's a distance. For Jack, let's start with Jack. His race is going to be split up into half the time, which we say 1/2 T, times the speed that he'll cover that time doing. He's going to spend half the time running and the other half the time walking. All right? And now, since we are looking for t, I'm going to solve this equation for t. So let's go ahead and look at what that does. I'll factor out a 0.5 t, and we're going to multiply that by r plus w. And then kind of using a little trick here, I guess. No, I guess I'm just going to divide by r plus w on both sides. So I'll have d over r plus w equals 1/2 t. Multiply both sides by 2, and we get that Jack's time, so the time for Jack, will be 2d over r plus w. That sounds complicated. We're going to get into simplifying that here in a second. Jill's is a little bit different. I'm going to switch colors for Jill. So Jill's is a little bit different because she's going to run half the way and walk half the way. So that means that half of her race, half of her entire race is going to be the running speed times time. And what time that'll be, we don't know. Excuse me, we don't know. The other half of her race, so you'd like put a comma here, the other half of her race will be spent walking. But each one of these is only half of her race. So we got to combine them to say that the entire race, I guess, yeah, so I want to add these, sorry. So I'm going to add these, and that's going to be r times t plus w times t. I'll factor out a t. And then divide by r plus w, kind of like I did before. And it's going to tell me that t, actually more specifically, Jill's time is going to be d over r plus w. So kind of a similar answer there. But we have to decide, based on really nothing, which one of these is bigger. Or I guess what we really want is we want the smaller, because these are times. The winner is going to be the one with the smaller time. With all these three variables in each one of these equations being the same, which one of these is smaller? Let's say that we're, it doesn't really matter, but let's say that we're going to go on a 10-mile run, and the running speed is 10 miles an hour, walking speed 5 miles an hour. And this is just to test it out, see which one's which. Maybe you know which one's which, and that's great. This becomes 20 over 15, and this becomes 10 over 15. So I hope it's pretty clear that this one is smaller, takes half as long, I guess, and that's actually the case. Now, which one is this? Well, this one was Jack's, and this one was Jill. So it turns out that Jill's going to win every single time. It's going to take her half as long. Not just that, but it's going to take her half as long. At least in this case. You should see if that works out all the time. So that'll be it. That's as far as I wanted to get. I do wish you luck on these tasks, and make sure that you're always thinking and trying to find ways to make these more valuable than just a math problem. That's not what I'm looking at doing here. I'm looking at how do we make these worthwhile tasks that really mean something. Have a good day. We'll see you in class.